All right, so let's get started. So welcome to the CERIAS weekly seminar series. Today it's my great pleasure to have Dr. Tingfang Yan from RSA Lab. Tingfang is a research scientist at RSA Laboratories, the security division of EMC, and her research interests include network security and data analysis for security applications. Tingfang received her bachelor's degree in computer science and information engineering from National Jiao University, Taiwan, and her master and the PhD degrees in electrical and computer engineering from Carnegie Mellon University. So with that, I hand it over to you.
Thanks, Dongyan. Thanks for inviting me. I'm really happy to be here. The title of my talk is Beehive, Large-Scale Log Analysis for Detecting Suspicious Activity in Enterprise Networks. And this is joint work with Alina Opri, Khan Onalilu, Todd Leatham, Will Robertson, Ari Jules, and Engin Kurda. So this is a collaboration between RSA Labs, EMC, the parent company of RSA, and Northeastern University. So most of what I'm going to talk about today are already published in our ACSAC 2013 paper, but this is very much work in progress, and we would really appreciate if you guys have any comments or suggestions or ideas for future collaboration. So an enterprise network is made up of multiple components. In addition to the users and the end hosts, there are servers that maintain the communication infrastructure, like DHCP and DNS servers. And there are also servers that support application-level functionalities, like web servers, mail servers, and database servers. But enterprise networks also deploy a variety of security products to protect itself from attacks coming both from outside and from within. And these security products include firewalls, intrusion detection systems, web proxies, authentication servers, and antivirus software. So all of these devices on the network monitor activities going on in the enterprise, and they generate large amounts of log data of different formats. Now, some of the logs do share common fields, like timestamps, IP addresses, port numbers, and protocol, but there is also information that is specific to the application that generated the log. As an example, logs from DHCP servers will specify the IP address that is assigned to this MAC address with this host name, and also an action field indicating the type of event, like an assign, renew, or release. Logs from VPN servers will include the user account that made the VPN login, the host name used in the login, and the internal IP address that is assigned to that VPN session. And when the session terminates, the corresponding log will include the duration of the session and the number of bytes transferred. Domain controllers log every authentication attempt to internal resources in the enterprise network. And so their logs include the username, the IP address of the host to which the user is authenticating, the ID of the corresponding Windows security event, and also whether that authentication attempt was successful. Web proxies intercept every HTTP and HTTP connection crossing the border of the enterprise network. And so their logs include fields in the HTTP header, like the domain name, the URL, the HTTP result code, the web referrer, the user agent string. But in addition to all of this, they also record the category of the remote site that's being visited, and also the website reputation score. So all of these log data are being collected and saved in a centralized data repository, which is called the Security Information Event Management System, also called the SIEM. So this SIEM takes as input these raw logs generated by these devices and then parses them into well-defined fields. And at EMC, the SIEM is running on top of a Hadoop distributed file system with a Postgres database front end, which means that when we want to access the data, we issue SQL queries to it. Now, together, there are 60,000 employees at EMC, and they generate about 1.4 billion logs per day on average, which amounts to about 1 terabyte a day. So this data is stored for 3 months, which means that we can always look back 3 months into the past to see past activities. Now, traditionally, these type of logs stored in the SIM are mostly used for compliance and sometimes for forensics investigation. So when a security analyst detects there has been an attack in the system, they can go back to the logs to trace the source and the propagation of the attack. The SIM can also generate simple alerts based on really simple rules like monitor user accounts with more than 5 failed logins, or monitor host that makes more than 10 DNS queries to non-existent domains. So they can support simple rules like this. But instead, in this work, our goal is to use these vast amounts of log data to automatically detect suspicious behaviors in enterprise. And in particular, these behaviors that we examine are guided by properties of an enterprise network, like the homogeneity of software configurations of enterprise-managed hosts and the business orientation of most user activities. So we want to profile user behavior over some time and then detect outliers that behave differently from the vast majority of hosts. Another important aspect of this work is that we're not really trying to automate detection in the sense that every alert is an infected host, but rather we want to reduce the human labor involved in incident response and forensic investigation. So we give the analyst a list of misbehaving hosts and also the context around their activities so that the analyst can actually make decisions and take actions based on those reports. So this is our goals in the paper. But it is not so easy to work with log data. For one, any technique that we develop must be able to process terabytes of data efficiently. The logs themselves are also extremely noisy. For example, the logging devices, they're located in different geographic locations, and they may or may not include time zone with their timestamps, and may or may not record timestamps according to their local time zone. There's clock skew that makes it difficult to correlate logs generated by different devices. Most of the logs use IP addresses as host identifiers, but DHCP allows multiple hosts to share the same IP at different times. The logs may be truncated due to database field length restrictions. They can be missing, duplicated, or arrive out of order. Now, in addition to all of this, there's also a huge semantic gap between what is recorded in the logs and what we really wish to observe. For example, there are over 500 types of Windows security events, and over 30 related just to log on and log off events. Now, in order to interpret these messages, we need an understanding of not only the LDAP protocol, as in this Windows authentication example, but also product-specific knowledge about how that protocol is implemented. Finally, we do not have ground truth about suspicious hosts in enterprise to evaluate our system, because the enterprise already deploys the state-of-the-art security products, and there are human analysts that work actively toward resolving new threats. As a result, no malicious activities are not observable because they are already blocked. So now, I will describe later, we instead evaluate our system through manual investigation. So we manually went through all of the alerts generated over a 2-week interval and then labeled all of them. There has already been a lot of related work on anomaly detection, on intrusion detection, on detecting stolen credentials, on malware detection, or on malicious domains detection. But to the best of our knowledge, ours is first to address the challenges of sanitizing, correlating, analyzing log data from an enterprise of this scale, and to detect both infected host and business policy violations. So I'm just going to give you an overview of our system, which we call Beehive. Given log data from various sources, Beehive has a normalization layer that removes some of the inconsistencies in the logs. So we standardize all of the log timestamps into UTC, create a mapping of dynamic IP address to host names over time, and also identify the user that is primarily associated with a particular host. After this, Beehive extracts features from the logs to characterize network communications from the enterprise. And we broadly group our features into 4 categories: destination-based, host-based, policy-based, and traffic-based. We represent each internal host as a feature vector, and then we cluster the host to find those with similar behaviors, and also to identify outliers that are just behaving differently from the vast majority of hosts. And we generate incident reports for these outliers that are later examined by a human analyst. So I'll go through each of these layers and then finally present results on the evaluation of this system. When an event is generated at an end host, it is logged by some network device. For example, your browser generates an HTTP request, and the web proxy logs this. The web proxy sitting at the border of the network, enterprise network, logs this. Sometime later, this log is sent and collected by the centralized data repository, the SIM. So we know that both T2 and T3 are included in the logs as two separate timestamps. We know that T3, the event collection time at the SIM, is always in UTC. But we don't know about T2 because time zone is not included in the log timestamps. And these network devices are configured by local admins with no documentation. And we can't just use T3 as the event timestamp because there can be arbitrary delays between when the event was generated and when it was collected. This can be minutes or even up to hours or days. So what we really want to know is the timestamp T2 in UTC. So how do we figure out the time zone of a network device? Well, we look at all of the logs generated by this device and then compute the time difference between T2 and T3. We round this to the nearest 30 minutes and then take the value that accounts for the vast majority of logs as the time correction value, which we can use to adjust all the timestamps into UTC. And as I mentioned earlier, most of the logs use IP addresses as host identifiers, but DHCP allows multiple hosts to share the same IP at different times. In order to attribute an event to the correct host, we have to create a mapping of IP addresses to host names over time. So to do this, Beehive analyzes DHCP logs and then create what we call bindings, which are represented by a 5-tuple. The IP address is the host name, the MAC address, and the start and end timestamps. Our last normalization step tries to identify the user that is primarily associated with a particular host. So this is so you can identify the user who's actually doing this and not just the host, going one step further. Now, lacking documentation about host user assignments in Enterprise, we instead leverage these domain controller logs. And these domain controllers are what we talked about a little earlier. They log authentication attempts to internal resources in Enterprise. So for every host, we can keep track of all the users that successfully log onto this host and the frequency at which they log in. Excuse me. And in this work, we're primarily interested in these dedicated hosts, which have a single user that's primarily using this host. And so we identify them by these hosts where a single user is responsible for the vast majority of logins to that host. So we first standardize the log timestamps into UTC. We create a mapping of dynamic IP addresses to host names, and so create a mapping of host names to users. So now Beehive can start the feature extraction step. And the first set of features that we're interested in are network communications to external destinations that have never been contacted by anybody from the enterprise before, or that are unpopular. And our observation here is that established sites are usually better administered. So malware communications are more likely to go to uncommon or obscure websites. Now, in order to identify what is new or unpopular, we have to have a set of destinations that we can use from the past to identify what is new. And we expect that after we observe communications over like a month or two, we will have a stable set of destinations that we can use to identify new ones. But to our surprise, we find that the number of new destinations does not decrease over time. even as the size of our history increases to 4.3 million domains over the course of a month. So in this graph, the blue line shows the size of our history growing over time. The red line is the number of unique destinations we see per day going out from the enterprise. And the green line is the number of new destinations that we see every day. So between 30 to 40% of all the destinations per day are new. So what are these new destinations? Well, it turns out that a lot of them are associated with content delivery networks or cloud services that often use these random-looking strings as subdomains, like in that example. Some of these new destinations are also just IP addresses belonging to popular services like Google or Facebook. So clearly, to make our approach scalable, we need to come up with some data reduction techniques. And the first thing we did here was to create a custom whitelist to filter out destinations that are popular with respect to our enterprise. So that is, we add a destination to the whitelist if it has been contacted by more than X number of internal hosts. And here we can see just an example, but you see the number of logs that Beehive has to examine go down as we increase this threshold X. And if we set this threshold to 100 hosts, then we can reduce the amount of logs that we have to examine by 74%. Another data reduction step we took was to fold the domains to only the second top level domain. And this is to deal with these random looking substrings that are used by cloud services or CDNs. So with these optimizations, we can reduce the number of new destinations from 145,000 to only 28,000 per day. So for a host, we say that its destination-based feature is the number of new destinations that it visited on this day, the number of new destinations that is not referred by somebody on a whitelist, so it's not referred by Google or Bing, it's just coming from some obscure site. The number of destinations that are just raw IPs instead of domain names, and also the fraction of these destinations that are raw IPs. And this is based on the observation that most legitimate services are referenced by their domain name rather than the IP address. Now, hosts in an enterprise are significantly more homogeneous in terms of their software configurations compared to hosts in academic networks. So we are also interested in cases where a host installs new software that may potentially be unauthorized. So lacking visibility onto the host themselves, we instead infer the software configuration on the host by looking at its user agent strings that's included in HTTP requests. So a user agent string tells us the application that made this request, its version number, capabilities, and operating environment. Now, in order to identify when a host uses a new user agent string, we have to keep track of a history of previously used user agent strings from this host. And to accommodate software updates, where the string is mostly the same, just the version number changes, we compute the edit distance between a new string and all of the previously seen strings from this host, and only consider it if it's sufficiently different. So for a host, its host-based features the number of such new user agent strings. Also unique to the enterprise environment is the enforcement of security policies on outbound communications. And at EMC, there are web proxies that intercept every outgoing HTTP and HTTP request and filters them both on a blacklist and a whitelist. In cases where the remote website is uncategorized or has a low reputation score, the proxy will present this agreement page to the user that requires the user to consent to the company's security policies before proceeding. So you have to click on that I have read link in order to visit the site. So in our Beehive system, for a host, its policy-based feature is the number of connections it makes and the number of domains that it contacted that are blocked by the proxy that are challenged, meaning that it got the challenge page, and those that the user actually clicked and consented to. Our last set of features looks for sudden spikes and bursts in a host traffic volume, which are likely caused by automated events. Now, rather than setting a threshold to define what we mean by a traffic spike, we instead look across the behaviors of all the hosts in enterprise. And we find that 90% of them makes less than 101 connections and contacts less than 17 domains during a 1-minute interval. So we use these as our thresholds in the current implementation. For a host, the traffic-based feature is the number of minutes in which its volume exceeds these thresholds. This is just a list of the features that I talk about in each of the 4 categories. So I went through them pretty quickly, but you can find more details in our paper or come and talk to me afterwards. So I talked about a lot of features that we want to use to characterize host network behaviors. But how do we put it all together? Well, if you may recall, some of these features require history, so we can identify new events, like the history of external destinations, or the history of user agent strings per host. So we have to build up these histories over some time, and then after that, every day, for every host in an enterprise, we create a vector that consists of these feature values. And then we cluster the host to find those with similar behaviors. And our motivation behind the clustering is that users have specific job functions in an enterprise, and so we expect to see hosts in the same department being clustered together exhibiting similar behaviors, while misbehaving hosts with unique patterns would likely show up as outliers. And just a little more detail about the clustering. Initially, all of the hosts are in one join cluster, and we just select a random point to be the cluster hub. After that, we select the node that is furthest away from the hub to be the new cluster, and then recluster the points based on their closest hub. We repeat this until the intra-cluster distance is sufficiently smaller than the inter-cluster distance. And we chose this algorithm because it does not require the number of clusters to be specified in advance. It is pretty easy to implement and fast to run. Now note that because we always select the node that is furthest away to be the new cluster, the order in which these clusters are generated are sort of a rough indication of how outlying they are. So in the order they were generated. Okay, so we clustered the host and then identify outliers that are far away from everybody else and create incident reports for them. After that, every day, we update the histories again based on new activity that we see on that day. So this Beehive system has been running on a daily basis in the EMC production network for a little more than a year now. Our code is certainly not optimized, but it takes about 7 to 8 hours to process a day's worth of logs. And this is running on a 2.4 gigahertz CPU with 48 gigs of RAM. So we want to evaluate how good this system is at detecting suspicious behaviors. But we don't have any ground truth because known malicious events are already detected and blocked by the various security products in the company. So to evaluate this, we instead resort to manual investigation. As we examined all of the hosts in the top outlying clusters every day for a period of 2 weeks. And our investigation process goes like this. First, we identify the distinctive features in that cluster, which means that we identify the features which made that cluster stand out, that made it an outlier. And then we look up contextual information about hosts in that cluster. For example, which domains they went to, the reputation of those domains, when those domains were registered, stuff like that. If we need to, we would go back to the logs that are stored in the centralized data repository, the SIM, and look up additional information about that host, or look up other activities the host was doing around the same time, just to gather more context. For those hosts that we could not confidently label, we gave to the Enterprise Security Operations Center for further investigation. And in this way, we manually labeled 784 hosts over the period of 2 weeks. And this is a breakdown of the labels that were applied to this host. It's a little hard to see. I'm sorry, it's so small, but roughly 25% of what we detected were confirmed to be malware or are suspicious. So these are stuff that were not previously detected by the Enterprise Security Operations Center. Another 40% of what we detected are business policy violations. So these are people doing instant messaging, streaming video, peer-to-peer file sharing, gaming, gambling, porn, trying to evade the network proxy. So stuff that you should really not be doing at work. 35% what we detected were what we categorized as other. So these are not necessarily malicious events, but certainly not human-generated. So for example, thousands of connections to sports sites, to news sites, to shopping sites, to online forums, to stuff hosted on the Google App Engine, and sometimes people mining Bitcoins. So we can't really say they are malicious, but they're just not human-generated, so we label them as the other. So in the following, I'm going to show you some of the examples that we found and kind of walk you through our investigation process. So on this particular day, the first outlying cluster, which means that the cluster that was most outlying, only had one host in it. And this host stood out because he contacted 490 new destinations that nobody else from the enterprise went to before. So what are these destinations? Well, this is a screenshot of what we found. But the first column is the domain names. And it turns out that they're all sort of randomly generated domain names. And this is a technique that is very popular within botnets called fast flux. So the bot would generate a whole bunch of random domain names that may or may not be valid. And the bot master only needs to register a few domains in advance to be able to talk to his bots. And in our 2-week study, we found hundreds of hosts that are beaconing out to fast flux domains like this. The second outlier cluster on this day had 2 hosts in it, and this cluster stood out because those 2 hosts made a large number of consented connections. And this means that the user was presented with that policy agreement page, and he actually clicked and went to that website and made thousands of connections. So what are those domains? Well, the first host is going to panel.takeedhost.com, which is a server for Minecraft, if anybody plays. So this is an obvious example of business policy violation by gaming at work. The second host is going to, it's a website related to SAP, business management software. So this is an example where we could have improved the policies whitelist by incorporating these business-related sites. Here's an example of something that was more suspicious. So this cluster had 3 hosts in it, and they stood out because they made a large number of challenge connections. And this is when the user was presented with that agreement page, but the user never clicked on it. But still the host kept going back and make thousands of connections, trying to go to that site. So what are those domains? Well, the third one is Google Docs, which happened to be blocked at EMC. But the first 2 are raw IP addresses. Instead of referring the destination by the domain name, they were just going directly to the IP. So I did a whois lookup on this first IP, and it turns out to be registered to some province network in China. So it's not really giving me much information at this point. So what I did is I went back to the logs and pulled up the actual HTTP connections to that domain, to that IP. And it seems that all of the connections to that IP had an URL with the same format. And it seems like there was a timestamp that is attached to one of the parameter fields. And it looked a lot like malware beaconing to me, but I can't really say for sure. So this is something that I gave to the Enterprise Security Operations Center for further investigation. Here's another suspicious example. So this host was also the only one in its cluster, and it stood out because it contacted a whole bunch of new destinations nobody else went to. It made a large number of block connections and challenge connections, but the user never clicked on any of them. So I pulled up the logs for this host, and I'm not sure how well you can see it, but it turns out that this is also somebody that's doing this dynamically generated domain name thing, except now that the DGA part is in the 3rd top-level domain rather than the 2nd top-level domain. So this is also something that looks suspicious, and we gave to the Enterprise Security Operations Center. This is sort of a user interface that we're playing around with. In the center big square in the middle, we show all of the outlying clusters on this day. And the location of the clusters is trying to represent the dominant features in that cluster. For example, cluster number 1 on the far right, the biggest one there, is dominant in both the destination-based features and the host-based features. And the distance of a cluster from the center is just the order at which they were generated. The order, because we always select the node that's furthest away to be the new cluster. The radial graphs across the top and the bottom are just trying to show more details about the feature values in that cluster. So each slice of the radial graph represents one feature. And in the highlighted cluster on the upper left there, you can see that it has a very high value in the first and the fourth feature. So this is trying to visually represent the clusters. And we envision this to kind of cycle through each of the clusters in turn. And when the cluster is highlighted, more details about host in that cluster will be shown on the table, in the table on the right. So this would be like, for this host, what kind of domains they went to, how many connections were made to those domains, and what the network policy applied to those connections. So this is meant as a tool for the incident response people. Here's another way we're playing around with to represent the clusters using turnout faces. So in this case, the facial features are controlled by the actual feature values. For example, the length of a face is the number of new destinations that the host went to. And the shape of the hair is the number of traffic spikes, for example. And because I know what's in here, I can tell you that cluster number 1, 6, 8, and part of 15 have all these DGA domains that people beaking out to a large number of random domain names. So which is fun. Our enterprise operation centers thought was funny, but they didn't really like it. So what I've just talked about here is just a subset of what actually built in the Beehive framework. So starting from the data and the normalization, we have a bunch of user behavior profilers that we want to use to look at different aspects of the user's activities on the network. So we already talked about the external sites that they go to and the user agent string installed on the host. But we're also interested in looking at the rate of data transfer to external sites so we can detect when somebody's leaking data out. We also look at the regular working hours of every user so we can detect activities that happen in the middle of the night or when the user is not usually there. We also keep track of all the machines that the user logged into in the past, so we can identify when he's accessing some resource that he does not usually access. So trying to look at different aspects, and you can use these profilers in different ways depending on what you want to detect, but apply different analysis methods to it. But the eventual goal of all this is to generate prioritized alerts that we can give to the incident response teams and to help them deal with these incidents. And of course, their feedback will help us refine the profilers, and maybe we can analyze trends in the enterprise about which hosts are more risky than others. Just to summarize here, this Beehive system that I talked about automatically mines and extracts knowledge about large amounts of log data collected in an enterprise. We present efficient techniques for processing these terabytes of data, and also profile user behavior over time to identify outliers that are misbehaving. And this system is currently running daily in the EMC production network, and we're in the process of setting up a direct feed for the incident response team so that they can deal with these incidents in a more timely manner. Thank you, and I'm happy to take questions now.
So, you're talking about clustering that you did with your data. And considering that your data is on Purdue, what kind of, how did you actually do clustering?
Well, we used the Hadoop cluster to query the data, but all the processing were done outside. So the data is a lot, but the models we use are quite small. So the feature vectors, there's only 15, so it's like 15 floating numbers per host, and the clustering is actually quite efficient. We didn't need a Hadoop cluster to do that.
clustering, you actually do it outside the service
Yeah,
bus?
we just used R for that.
Did you say you use R?
Yeah.
Okay. I'm actually in this, I have the same issue. I mean, so I'm wondering, what library you actually use.
Oh, I'm sorry. This is not R. This is just the Python implementation.
Okay.
Yeah, yeah.
And do you know a sample of your data structure that you use? If you, I mean, if it's okay, that would be actually great.
I can tell you the format sort of, but I don't know if we can release the data
No,
set.
so just if you can just tell the format, that's great as well.
Yeah, so I use Python for most of this, and so they're stored as Python pickle files, and I use dictionaries a lot for them. So for example, the new destinations would be like this host, indexed by the host, pointing to domain name, number of the timestamps, and whatever attribute I want to save. Yeah. Yeah, thanks.
So can you give us a little bit an idea of the scale of the data that you're dealing with? Either the raw data or maybe the flow. So are you doing everything, all the processing offline, online, things like that?
Okay. So the data is stored in this centralized database, and it's being dumped in there in real time. So not a real time, but like 5-minute lag, 3, 4, 5-minute lag. But our processing is done daily, so in batch mode. Today we look at previous days worth of data, and together it's about 1 terabyte a day. But we don't look at everything. So for example, there are like firewalls that we don't look at. There are some DNS logs that we don't look at. So mostly we focus on HTTP traffic. That's about 300 to 400 million logs a day, I think, but it's a lot. In terms of volume, it's a lot, like in terms of the bytes, because it has all these fields like the URL, the domain name, the user initiating the web refer. So like that, I would say it takes the bigger chunk out of the 1 terabyte a day. But everything is done in batch, so 7 to 8 hours per day. Yes.
What about the efficiency of the cluster algorithm? And do you improve the cluster algorithm?
The clustering algorithm itself runs in a few seconds, so that's not our main bottleneck. Is that your question?
I mean, the algorithm, the cluster algorithm is in the normal or has been improved in the system.
So the clustering algorithm, I think it's not really a standard clustering algorithm. It's mostly like a way to initialize k-means, because we don't know for k to pick. So this is a way to quickly do that. And you're supposed to run it over multiple iterations and kind of do the average. But for us, it's usually the case that like 99% of the hosts fall in one giant cluster, and then we see like 1% outliers. So I tried randomizing the initial point, and it doesn't really make much difference. So we run it once, and it takes a few seconds, because we're only mainly interested in the outliers. So this was sufficient for us. Thanks.
So could this detect something like a rogue device, like someone plugging in a router they brought in, or does it only really detect things that are generating active network traffic?
We only look at network traffic. So if it's just sitting there not doing anything, then we can't. If it's somebody bringing a router and plugging it in, we probably won't see it anyway, because that router is not instrumented to report to the data repository, right? It doesn't send any logs there, so we don't see it.
So you're not like actively reaching out and scanning your own network for
No.
SNMP or anything?
No, but I think that problem is called shadow IT, which is like IT that you don't see, and it's actually a very interesting problem that we don't know how to deal with yet. Stampede upstairs.
I'll ask one more question. Also, can you tell us, because I'm more interested in the setup, like for example, how many hosts are we talking about, or how many services,
Okay.
heterogeneity in terms of different I mean, I saw some Kerberos there, so I figured out you're running some Windows, but
Yeah.
I was just curious if you can tell us a little bit more about that.
Sure. So this is an enterprise, right? So it's mostly Windows. The software is mostly pretty much homogeneous. I would say like 93% of the hosts have the same image. The rest are like, some people have Macs or Linux, and some are servers. The number of hosts we're talking about, I think it's around 120,000. So yeah, it's like 60,000 employees, but that's the ones that we could see in the log. So there were a lot that are not reporting. So I expect this number to be much more. But in this, we focused on those hosts that have a primary user behind it, so like end hosts, not servers. And those are like 87,000, I think. Like 70,000. I would just ballpark it there. Yeah. Yes. Thank you so much.